Hey everyone, how are we doing? It is afternoon office hours. I think Tiffany had the first one. She'd asked about it during the last office hours. So we're gonna jump into that. Mewbot's already awake. We're gonna re-wake up Mewbot. He's pretty good. Says some people are watching. Good to have everyone here. How are people doing this afternoon? We're gonna go in, do some questions about wartime stuff to start. Access denied. No, I've lost my MyPearson access. Gotta reload it. Gotta reload the full MyPearson thing. We're loading up some MyPearson right here. One moment as we get this going. I don't know why. The Epic Pen does weird stuff to my screen. It makes it have problems. I like Epic Pen, and then it just causes issues. Close all this down. How did I reset my computer yesterday? A lot of things open. So many things. Okay. Let's go find the war problem right here. Who all is here? Good. Kayla, good to see you here. I got both my kids down for a nap and I feel like a warrior. Nice. Just being howdy. Good to see you here. Got some howdy for Texas. My brother has 2 kids and that's a lot of work. Like I could not imagine. We'll throw some points out to the chat. I can't imagine having kids. Like I know I'm going to be 40 in days. I don't know, 70 days. About 70 days and I'll be 40. That's how numbers people talk. In 70 days, I'll be 40. I just keep thinking it's going to be here before I know it. I got to stop thinking that. Got to stop thinking that as we start the problem here. A certain story describing weeks of a long war and their injuries. Let's go check that out right here. And their causes. Wait, I think you might have a different one. There's 2 of these. I think the other one says causes. So let's go find that one. Because there's 2 war questions. You got to have a lot of war questions, right? Yep, got it. Here's the one we're doing right here. My oldest mini speech in his Veterans Day programs. Aww. There's a Veterans Day program? I don't know what that is, but that's really cool. Congratulations to your oldest right there. Congrats. That's really awesome. Happy news. Aww. As I see my nephews get older, I'm just like, man, time. It's like my parents probably looking at me now and they're like, oh, he's a man. Brian's old. When we do the null and alternative, what is our trick? What one word do we put between the null and the alternative right here to do some practice? So let's get some practice in. What is the one word we put between the null and alternative right here? I'm just going to put one word between these. I'm going to say like the type of weapon and the injury site are what of each other. Now, it might not follow this. I hope it does. But what one word? Independent right there for 100 points. That's how we do the null. Which means Rock knows
it doesn't matter.
These 2 really don't matter. They're independent of each other. So you just put one word that the 2 are independent of each other. So let's go look at the answers and see if one of those follows that. Site of injury and weapon are independent. Site of injury and weapon are not independent. That's the complement right there. So we got question 1 done. Now this part is a little more tricky. Jump is going to super help for the next part. You could solve this all by hand. We have to find all of the expected counts according to the null. To do this, you could go here and solve each individual one. Let's show how to solve one of these by hand and then use jump for the rest. To solve the expected count, and usually we do the smallest to check the smallest cell count condition, we'd go here and we do row total times column total over grand total. I'm going to take the smallest row total times the smallest row total, column total, row total, and divide by the grand total. That is row total times column total divided by grand total. And this is equal to a singular expected cell count. Now we can solve out a whole bunch of these expected cell counts, but this is the smallest one. And it would be associated with this cell right here, which is actually the smallest. That's just what can happen sometimes. So the expected cell count for that one is 11 times 31 divided by 140, and it's 2.43. So that 2.43 would go right here. Does it round up? Watch out. Ooh, it does round up to 2.44. There we go. That is, hey, Parker, great to see you here. That is one expected cell count by row total times column total. We should put a little times right there. If you have a question, let me know. Row total times column total over grand total. And that is how to get the expected cell count for ground rock injuring somebody's limb. But what we're going to do is we're going to take all of this, copy it to the clipboard, copy it, Control C, and then we're going to go over to jump right here, go to jump. We're going to go to File, New Data Table. I'll pause right here. Make sure to copy your data. Go to File, New Data Table. File, New Data Table. We're wearing some Dig Dug shirt today. File, New Data Table. And inside of the new data table, we're going to edit, paste with column names. Make sure to paste with column names because this one had column names when you copied it. There we go. If it looks like this right here, it is wrong. So make sure to paste with column names. This is the right, this is the wrong. Start over if it has the error. So now that we've pasted with column names, we have our data inside of JMP. We can see the same sort of table we have, but we're now going to have to stack it. This is just how the data came in. It didn't come in properly. So we're going to go to tables and go to stack. I'll pause right here. So we should have all the data in JMP. It should look the following way with red, blue, blue, blue. And now that we're here on tables and stack, that's tables stack. We're just going to double click the blue columns. Click, 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 click. That adds them. Click, click. So you should add the blue columns right there such that we see body, head, neck, and limb all over there that are going to get stacked. That means we're going to stack them on top of each other. And once we stack these on top of each other, we'll get our new table, which we'll do the analysis on. There we go. And there's our new table. We're good to go. New table completed. We have the data ready to go. And we can see right here the weapon used and the area it hit and the amount of observations. This is count data once again because we have counts of observations for individuals. 4 individuals were hit by an arrow in the body. Someone took maybe an arrow to the knee right there, it seems like. But these are the different weapons, and these are the areas of injury, and then these are the amounts of observations. Like 57 people got hit by the body, got hit in the body by a sword. Not good. Let's go to analyze fit y by x, because we have 2 variables right here. It might look like we have 3, but we only have 2. So we're asking, what weapon were you hit by, and where were you hit by it? So maybe the type of weapon, which is the label, explains where somebody got hit by it, but make sure you put in here the frequency. This is under analyze fit y by x. We're just adding in the frequency right here. So we need to make sure we have this data right here because this is the count of the observations. And this is what weapon were they injured with, explaining where they were injured. So maybe there's an association between like someone has a bow and arrow and they shoot at you. Maybe you're more likely to get hit in a limb. I don't know. This is war. Someone has a sword, maybe they're more likely to hit you in the body, which maybe we'll find out. Let's go ahead and hit OK right here. And here it is. It looks like sword was more likely to hit someone in the body. Or wait. Body is more likely to get hit by sword, we should say. Given someone got hit in the body, they were more likely to get hit by the sword. Let me look at one thing real quick. To make our lives easier, I'm going to redo this. So I'm going to go here to redo relaunch analysis. I'm going to explain why. I'm going to the red arrow at the top and going to redo relaunch analysis. And I'm just going to switch these. I'll explain why. The reason I'm switching these is because I want it to look like their table, and they did it the following way. So I just reversed it. And if you look right here, we have the same order. I'm going to make it so we can see everything at one time. And we have the same order to the data that they have. So if you look at this right here, let's remove out, we'll just keep it the way it is. We have arrow, ground, rock, limb? That is an error on my Pearson's part. I got 2 things to contact them about. Limb is not a weapon. I mean, you might say this is a weapon, but no, that's supposed to be sword. My Pearson, that is an error, like your error this morning. And so body, head, neck, and limb over here, but that should be sword. So now you can see right here, we need the expected counts. I'm going to remove out all of these by just unclicking them. I'm just kind of going overboard right here because now I'm only going to put in the expecteds. So these are the only values we're looking for, and look at what I see right here. Look at that. Do you remember that? That's that number we calculated a moment ago down to decimal place accuracy, so we can get all these numbers right here. I wonder if we can format the table. Apparently, we might not be able to. I wish we could, but I'd love it if I could just take this table and put it to 2 decimal places. But that's got it. There's all of our answers right there, everything we need. 5.94. Let me make this so this can go over here. And we're just going to take these answers, really. We're going to take these answers right here and put them in to the table. There we go with this. There's those answers. And here's the arrow body. Please tell me if I get something wrong right here. 5.94. Very easy to make an error. 4.18. And, you know, you could have worked these all by hand. It's good practice for the test. It's just very repetitive. But probably in the amount of time I did it, you could have went through and did all of these by hand, doing row total times column total over grand total, and work each individual one. Really good practice to make sure when you get to the test, you solve them all out properly. 53 point, wow, we expect a lot there. And the reason you would use jump is because the next question is not one I would solve by hand. Doing this full problem by hand would take a good bit of time, but it's much easier to do jump. So there is the expected cell counts for how many individuals we would expect given the null is true. The next question is, what is the chi-squared test statistic? And that is the Pearson chi-squared test statistic right here. That is the sum of all the cell chi-squareds. So here's the cell chi-squareds. Yeah, having a good day. Good day today. And the sum of all the cell chi-squareds, 0.6, 0.3, 3.3, 0.8, 3.4, 0.8, all these would add up to 9.59, 9.959, 9.5, oh my gosh, 9.96. How many degrees of freedom? Now, I'm going to pause right here. This is where degrees of freedom are one of my favorite things to calculate. It's one of the easy questions on the test. We love this. Who knows for 100 points how many degrees of freedom this has? So it's probably said it on the other screen, but this is a what by what, which means it has how many degrees of freedom. So pretend this is a test question right now, and how many degrees of freedom does this have? If you look at that right there, you'd say, oh, that has this many degrees of freedom for the chi-squared. So this has how many degrees of freedom? Does MuBot know chi? I think I put that in. This has how many degrees of freedom for the chi-squared? Who knows how to get the degrees of freedom for the chi-squared? So the rule is, MuBot does know about it. The rules for the degrees of freedom for the chi-squared are you take the rows, there's 3 rows. You take the columns, there's 3 columns. You do rows minus 1 times columns minus 1. Right there. Great job, Tiffany. There are 4 degrees of freedom because there's 3 rows and 3 columns, and that's 4 degrees of freedom. Now that tells us which chi-squared we are using. Now, Jump's already done all the work for us to get the p-value, but if we had to do this by hand, we would have to go to the chi-squared and enter in 4 degrees of freedom. It's already there for us. So we go to the chi-squared, we enter in 4 degrees of freedom, and we put in the chi-squared test statistic value. And we should on Jump have about 0.0041. And let's go look at our Jump data. There it is right there. So let's show this at the same time because this is the graphic showing the p-value. There's the chi-squared test statistic. It is a chi-squared with 4 degrees of freedom because 3 times 3, or 3 by 3 is 2 times 2, 4 degrees of freedom. And this is the chi-squared curve we are using, and it's going to have a p-value of, Jump calculates it a little more exactly, but 0.041. And when you think about this, degrees of freedom work the same way here. If you have more degrees of freedom, that curve starts to look more normal. But the chi-squared is a right skew distribution, so it won't look normal. So these are a little hard to calculate in your head if you're trying to calculate what would it be. And so the p-value is 0.041. 3 decimals. There we go. And what do we do at the 0.05 alpha level? The p-value here, Tiffany, is high or low. That could be right. That could be right. So your p-value, like mine, is high or low. So using an alpha of 0.05, is your p-value and my p-value high or low? Because if it's low, we reject the null. If it's high, we just let that null fly. We just let that null be. Yep, that sounds right for you. If the chi-squared is that large, you would have a larger chi-squared goes to smaller p-value. If the chi-squared is larger, which your chi-squared is 14.395. Yeah, and then Jump's going to calculate it more exactly. So it looks like you are on the right track. Yep. So that looks to be our p-value. And since your and my p-value is low, what are we going to do? Our p-values are low, so what should we do over here? What do you think we should do? Our p-values are low. Since the p-values are low, we're definitely doing this. It's like, oh, these p-values are low. We should what the null. The p-values are low. We definitely... So I always like to answer these without looking at the answers. It's like my p-value is low. reject the null. That means I reject the null hypothesis and I have evidence. Reject null, yeah, exactly. I conclude that injury and site are not independent. Remember, our alternative is that they're not independent. So that would mean there's evidence for the alternative. So I reject the null and we have evidence. I conclude that there is evidence for the alternative that they are not independent. Woo! We're never getting anything wrong again. That's got it. Great work right there. We reject the null. There is evidence for the alternative that they are not independent of each other. So, got so much lights and shading and everything going on. Let's hop back to the main screen. Excellent work right there. I think we have another 2-sample t-test. Can we go over chapter 7 problem? A sports reporter on the baseball and football players' average ages. Let's go check this out. It was interesting. One semester, Julio was taking the class, and we were talking about like the average age of sports players. And it's so cool when you have like a former professional baseball player, talking about the average age of sports players. I should call Julio and see how he's doing. Good stuff right there. Next question. Average age of sports players. See, we know my Pearson can make an error. Here we go with sports players. Let's go check out the average age of sports players. Here we go. So we have a sports reporter analyzing it. Wait, what is this right here? It says Y bar. It says S. What is this notation? It says N. Well, while you think that over, I need your help to know what this notation is. Because they're going to call up sports players, and then they're going to ask them these questions. It also gives us the degrees of freedom. Very nice of them. So, what are those notations? What's the deal with N30, N31, Y bar this, Y bar that? So they did what? Oh, they selected 31 football players. Yep. We can do that next, you bet, Tiffany. And so they selected 31 football players, 30 baseball players. And it's going to be pretty important. I might have missed one little thing, because how are they doing their test? They are setting it up. Which mean is which? Let this be baseball. So it's baseball minus football. Okay. Nice job, Kayla, right there. 100 points. Great work. We have standard deviations of each group and means for each group. Exactly. S means the standard deviation, like the variation within baseball player's age, and Y bar means the variation Y bar would be the average age for either group. So Y bar, the average age of a baseball player, Y bar, the average age of a football player, and then this is like the variation. So there's more variation in baseball players' ages. Like baseball players have more spread to their data. Their ages are more spread out than football players, according to this data right here. Don't know if that's true. So we're going to do a null and alternative. They want to test, let's see right here. Suppose the researcher decides to test the hypothesis. I think they're just seeing if they're, a researcher suggests that professional baseball players must be on average older. Oh. And the baseball players are going to be considered the first mean. And we do see in the data that baseball players are older, but that maybe it's just this sample, right? Maybe it's just variation in the sample. But if we were to take these means and baseball players were older, this difference would be what to 0? If it's true that baseball players are older than football players, this difference would be what to 0? So just put one symbol in the chat, because if it is true that baseball players are older than football players, and this is the alternative, then we would see a difference that is what to 0. If it is true that the average age of a baseball player is older than the average age of a football player, the difference between them, baseball players' ages minus football players' ages on average, would have a difference that is what to 0. If baseball players are older than football players on average, we would see a difference. The true difference would be what to 0. The true difference between these would be what to 0. Be greater than. And the whole reason we focus on writing these is because if we know the alternative or the null would just have the equal sign. So say it with me, the null has the equal sign. The null has the equal sign. All we changed right here was the sign. So we'd be saying, the true difference between their ages is equal to 0. There is no difference. And we're looking for the alternative that the true difference between their ages is greater than 0, which would mean baseball players are on average older than football players. So when we run this test right here, we need to run the test using the following equation. Y bar 1, I can't write. y bar 1 minus y bar 2 over square root s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. And this is equal to a t with the degrees of freedom 552.74. Now it tells us this in this problem, so we do get the answer to it, but we could use the t degrees of freedom applet to get the answer. We would give you things like this on the test. Like this is a very fair test question right here to find the t statistic, and that's just telling you which t you're using. The t degrees of freedom applet that Charlie Quick posted would allow us to put in here the following values and get the degrees of freedom. So going over here, I'll try to get it on the screen at the same time. We would go right here. Oh, let's go a little bit smaller. There we go. We have a sample size of 30, a sample size of 31. Let's see how my Pearson did. We're checking their work now. And the degrees of freedom are, and that looks to be, yep, they rounded it properly. It looks like there it is. And that's how we'd get the degrees of freedom. And you would not solve for this on a test. This would not be solved for on a test. Oh, wait, I don't know what that means, Kale. So here is the equation, and that's just to get the degrees of freedom, telling us which t we are using. So now all we're going to do is just plug in the numbers. We're going to take the mean for baseball. Oh, wait. They're trying to show baseball is older? Baseball was not older. Is this really a counterintuitive one that you get a higher p-value? It's just that professional baseball players must be on average older. Oh, wait. That's not the mean. 27.55. Can't make mistakes today. This morning, Kayla, we were double checking my Pearson. I swear my Pearson has an error. We were doing the bike route question, which I've done tons of times. And the question it didn't work out. We solved it inside of a R, and we got a very exact answer. So I'm blaming it on my Pearson. I do make errors. I almost made one there. It's not too bad. The equation's not that bad. Let's go solve the standard error on the bottom right here. 3.98 squared is basically 16 divided by 30 square root, and that's that. 2.88 squared divided by 31. I did square it, right? I did. And then we add to it. That's right. This. Okay, cool. And then we square root it. Okay, good. 0.997. So that means the difference here is close to about 0.8 or so. Can we reduce the whole thing down? No, we can't. So the bottom of the equation is 0.9971. And the top of the equation is just the difference between the two right there, which is 27.55 minus 26.7. 0. So this is going to be very close to that because they'll do like 0.86 or something, or 0.87. Hey, Morgan, great to see you. If you got questions, let me know. Ask any questions you got. We'll work them out right here. And we divide that by 0.9971, and we get 0.852. And now we need to go to the t-applet. Can we go over the Chapter 17 quiz? Research to start how to analyze drinking size? Yeah. I think Tiffany's got one before this, but then we'll do that one next. Jordan, you got it. Great question. Thank you so much, Jordan. Tiffany's got the next one, but we got tons of time, so we'll do Tiffany's, and then we'll do Jordan's. And Morgan, if you got a question, let us know. So now we're going to take this t statistic we just found. We just solved everything right here to get that t statistic right here. And so we're going to go over to the t-applet now. And remember, we need to know the degrees of freedom. The degrees of freedom for this problem were, I had it up, and then I removed it. The degrees of freedom for the problem are 52.74, and that tells us which t we are using. So 52.74 is the t. And we are testing the greater than alternative, and then our t statistic that we found is the following value right there. And there's the p-value, about 20%, 0.199. And this should solve everything in the problem because we're not going to reject the null. This is a very likely occurrence. So the differences between the two means are pretty small. That's what it means to have a high p-value. And we were testing to see if there is a difference greater than 0. The t statistic we calculated was the following, round to 2 decimals. There's that. The p-value was to 3 decimals, this. State your conclusion. I do not reject the null. I fail to reject the null. There is not evidence, and that should do it. What is going on today? Let me double check our work. It has to be this whole region right here. What did we do? How did we carry our numbers wrong? Yeah, it is this region. What did we do? Kayla, I need to double check my work. I cannot write numbers today to save my life. 3.98, standard deviation, 2.88, 31. I had to have solved the standard error wrong. It has to be that, and that made the p-value wrong. So let's check this out. 3.98 squared is this, divide by 30 is this, that's got it. And then 2.88 squared is this, divide by 31 is this, add to it is this. That's the problem. So now the z-score is going to be about 0.95. So the z-score is going to be about 0.95. I'm just going to I'm just mad at myself. It's going to be the t-score, the t-score. And the p-value is going to be about... what did I do? Yeah, so now we're close. Got it. Okay, so Brian can't math. I don't know what I did. This number down here, somehow I got wrong. So 8919. Man, I'm just... No, it's me entering numbers into the calculator, not checking my work. Work everything twice. This is written correctly, but then I didn't... I think I'm like second guessing myself too much these days. That's not the t-value. That's the... So we need to take 0.85, which is the difference, divide it by this. The t-value is 0.952, so I did guess that correctly. And now we take the t-statistic and double check your work. 0.952, and the p-value is 17.3, which is close to my guess. And there we go. What did I do? What did I do that first time? Did I not square root something? Or did I not square something? I don't know. Did I not divide something? I'll have to rewatch the video, but if you solved... So nothing I did theoretically was wrong. I just didn't solve a math equation correctly. And that's just the biggest error you can make, is like not solving a math question correctly. Also notice that the t statistic is close to 1 and the p-value is close to 16. So that's how we can usually guess it pretty close. But, oh my gosh, what is wrong with me in my math today? I am ready for the weekend. Hopefully everyone else is ready for the weekend. No! Let's continue on. Check your math. Brian can't math, apparently. Algebra is just the hardest thing. I think I'm like worried about it these days because I got one wrong. Like, I don't know. I go a whole week getting nothing wrong, and then it's like the last 2 days have been like, I think I need more sleep. Okay, let's hear. Can we do this one? Each of these tests in the chapter uses a what? I think it's probably gonna be the t-distribution, Tiffany. Is that what it... Tiffany, for your question, you're doing... No, you're using chi-squared. You're doing chapter 19, right? So I think I can basically answer that one. Chapter 19 uses all chi-squared, right? I think it basically answers it. Every test in that chapter, chapter 19, is the chi-squared. So every test will use the chi-squared test of independence. So it's going to use the chi-squared distribution. Does that sound accurate to the one you're working on? Chapter 19, yep. So every test will use the chi-squared. Does that sound right? I think that answers that one right there. Every test uses the chi-squared, right? So we'd be using the chi-squared distribution to solve them. I think that should be it. Yeah. Great job, Tiffany. Yep. Everyone will use the chi-squared model. And let's see right here. Research invest. We're gonna destroy this one. Here we go. Yep. It'll be the chi-squared. Chi-squared. Researchers investigate the size of a drinking glass. Let's go check out the drinking glass. Here we go. So it's a very similar problem to the one we just did a moment ago. We're going to get this one right. And you'll notice you get the summary statistics for how many samples there were for each of them. And then we have to find the t-statistic and the p-value. So when we run this right here, we'll be using the same equation we used a moment ago. So make sure to put the numbers in properly and to double check your mathematics, because sometimes you make a small error on solving something. So we're going to take this and take our data right here. We have the drinking glasses are written as, which one is drinking glass 1, where mu1 is the population mean of the small glass. Like of adult beverage right there. The mean for the smaller glass is, so the null hypothesis, what would we say about the two means? What do you think the null will state and have about the two means? The null hypothesis will state what regarding the two means? Like it'll say like the mean for this drinking glass is what to the mean of the other drinking glass. And you can think about the way we always write the null. I usually write it in statistical notation. You can see it on the previous problem where we write the null and it has the what. Like the null will always have this. So we were saying basically like the amount of drink someone puts into a glass, rock, nope, wrong one,
It doesn't matter.
is going to be independent. We won't write independent here, but we'll say, you know, it doesn't matter because it's going to be the same. The null has the equal sign, so the null has the equal. And does it change? So does the drinking size change? And that's the sign of the alternative to say it's not equal. So let's say is the same and is different from. So that's what it means to change. We're going to say it's not the same. And let's go and grab the data and run the test. We're just going to destroy this one. Let's do it. So not R. We're not going to use R for that. So to run this right here, we have our data. And you know what? Actually, I might have a way of doing it. Yep. Message me and I'll get it fixed. You bet, of course. For this one right here, we're going to use the following equation. I get decimals wrong all the time. I just do it to let people know it happens. And so we're doing a t with a certain amount of degrees of freedom. We'll find that in a little bit. Is equal to, you know what? Let's find that now. We need to go to Charlie Quick's website right here. And Charlie Quick has a quick calculator for this. You could do this equation by hand, but you won't do it on the test by hand. A lot of software will do this for you. And we could do it inside of multiple different softwares. But here is the applet we're using. It's in the chat if you're looking. And we're going to go right here, grab the data, put in the sample sizes of 30, 30, and the standard deviations of 1.78. Can you do it once more when you're done with the above questions? Which one? Can you do it? Yeah. Here, I'll do it during a pause screen. You bet. 2.82. And there you go. This is a T. Oh, you can't see it. This is a T with basically 49 degrees of freedom, which tells us which T we are using when we go over here. So let's just take that right now, and I'll put the T applet in the chat. We're just going to take these degrees of freedom because that tells us which T we are using, and we are using a T with that many degrees of freedom. Remember, the degrees of freedom tell you the shape of the T, and so we are using a T with this many degrees of freedom. So that is the shape of the T we are using. We'll come back to that here in a little bit. So now that we know which T we are using, we need to find that T statistic by doing y bar 1 minus y bar 2. Now this is set up properly with the first group and the second group over the square root of s sub 1 squared over n sub 1 plus s sub 2 squared. It's very similar to your s over square root of n, but they're squared, so we can add them together. Student inertia, of course, yeah, definitely. I think we got enough time today, you bet. And so right here, let's go ahead and take your, so double check my mathematics. No more errors today. There we go. And there's y bar 1, so it's going to be a negative difference. Yep. And then we go square root, and we go here to s sub 1. And we go here to n. And then put over n, s sub 2 squared. Okay. And let's solve the bottom. 1.78 squared divided by 30. That's that. It's going to make an error. Times that. Divide by 30. Plus the other one. Square root 0.6088. So let's take the difference of the top two numbers. Got that copied. 4.83 minus 6.57. Negative 1. There's that. And then let's divide it by what we have stored. And there's the z-score. The t-score. Oh my gosh. Don't call it a z-score. It's a t-score. 2.86. And the p-value should be pretty much guessable at this point. So we're gonna say, my Pearson, we can do this better. than you can, unless it says 4 decimals. And I say, oh my gosh, you really want some decimal place accuracies. How dare you with those 4 decimals? Tough one to guess to 4 decimals. It also wants our t to 3 decimal place accuracy. And there's that. The p-value. Now we're doing the does not equals test. The p-value to 4 decimal place accuracy. For the does not equals test. Gianna, great to see you here. Ask some questions if you got them. Let me know. So we will find this, show it here visually in a second. But I am guessing it's going to be about 0.0058. Now that's my guess. Let's see how close we were. We need to go to our applet. Remember, we brought this up. We put in our degrees of freedom, and we are doing the two-tailed test. And let's put in the t statistic we found of the following. And I think we should be fine on the decimal. Actually, it looks like I was close enough on my guess, 0.006. This applet looks to, I think we're fine. Let's see if it likes it. How dare you, my Pearson, if you say this is wrong. I'm going to put in the 0 after that. This one only goes to 3 decimal place accuracy. If we see, and one thing, if you have small decimal issues, let us know. So your conclusion, I reject the null. The data provides sufficient evidence that there is a difference. Now, the reason we're saying there is a difference is because of this. You know what? I am not going to let my Pearson win on this no matter what, because I'm going to go right here. I'm going to go to my thing, and I'm going to double check. If you get this wrong, let me know. I'm going to go to QT, and the degrees of freedom on this were, I'm going to double check my answer, because I am not getting anything else wrong today. Watch me get it wrong. There we go, on PT for the probability. And there's that times 2, and it's got a 2 at the end of it. Let's see what it would have accepted. Let's see if it would accept that. So that is the exact decimal place answer. There we go. Would it have accepted this? Would it have accepted the 0? It would have. And would it have accepted my guess? Didn't I say, was this my guess? I think that was my guess. Oh, my guess would have not been accepted. My guess was close, but it would have not accepted it. Would it accept rounding up? It would not. Does it just want the 4th decimal? No, it won't. So you got to be pretty close. That is some pretty crazy decimal accuracy. Let us know if you were to get this wrong due to decimal accuracy. It's being really nice on the last decimal there. That's the exact, but it does let you put in. But I think if you don't put in the 0, I think it will get mad, which is so weird. Oh, it still counted it. There we go. So we did get it correct, but to 4 decimals is pretty extreme for a p-value. I mean, if it's below 0.05, 0.06, 0.062, same sort of tomato. And I'm using R here to get a much finer calculation on that p-value because the other one doesn't report it to the decimal accuracy that I wanted. But that's got it. I think we had another question right here. Let's go back to the main screen and check it out. We're not getting anything else wrong. We're going to double check the work. Let's see right here. I think, was it Tiffany the next one? Can we do the Chapter 7 Queen? Researchers, exactly. And then Tiffany wants the question. And Gianna, if you have any questions, let us know. Students in an introductory statistics class were classified by birth order when they attended college. And this is homework question 3. Let's go check it out. 2 seconds here. I got to switch the assignments. Nothing wrong today. That's what we do. It's like a Dark Souls run, 0 deaths. If you've played Dark Souls, you know what I'm talking about. I need to go back and play more Demon Souls. Good games. No, Bloodborne. That's what I'm playing. Bloodborne. Good stuff. I was playing it, and then I got distracted by Ed McMillan's games. Hey, what's up, Rachel? Great to see you here. Drop a question in the chat. We're about to do some Chapter 19 chi-squared. So drop a question in the chat. Say, hey, can you work this problem? Can you explain this topic? And we'll do it because it's open questions after this, so we'll need some questions. Let's go check out Chapter 19, birth order and people's majors in college. Now, I'm going to give you one of the easiest test questions. Oh, here, we'll do it between the next screen. Remind me, Tiffany. Remind me at the next screen. Oh, I'm on top chat. Remind me on the next screen. I'll go change it on the next screen, Tiffany. Like, we'll do it on the next thing right here, or the next little switch, because we'll have this done in a moment. So when we do this right here, what test are we doing in Chapter 19? The chi-squared what test? The chi-squared test of what? Like, boom, we can ace this question pretty quickly. What test will we learn about in Chapter 19? The chi-squared test of this. It's like when we write the null hypothesis, we always say that the two are what of each other. You're awesome. You got this. 100 points, everyone in the chat. We always say that the two are independent. So we're doing the chi-squared test of independence. We're not doing a homogeneity or goodness of fit. So we got that chi-squared test of independence. State your null hypothesis. What word do we use? I'll say it. We use the word independent. So if you remember right there, we were talking about, are they independent? So I like it when my Pearson does this. You might not see it. We might have to think about this, but the null will be that they're independent of each other. That somebody's college that they go to, like at a school like UT, they go arts and science, professional or social science, the college they go to is independent of their birth order. So let's see right here. Oh my gosh. Choice of college is independent of birth order. Boom, done. Once again, that's the easiest way to do it. Is, are they independent? That is the null. It means they don't give you information like somebody's birth order and their college choice. It doesn't matter. You knew that's going to happen right there. It just doesn't tell you anything. Now, the easiest way to do it is to put a not right here to say choice of college is not independent of birth order. Now, I don't know if they're going to do that. Choice of college is independent. Nope. There is an association. So it would mean they're not independent. That means the two are associated. Like if you know someone's birth order, that would give you information. So I don't like writing it this way, but that is the way they're going to write it right here, because I would just like to say the null is that they are independent. The alternative is that they're not independent. And that's the easiest way to do it. That's the easiest way to do it right here. So they didn't go the easy way though. What are the conditions? Condition 1. And they're splitting it apart into a random and independent. So they're just calling it, like, is it independent? Is it random? They're splitting apart. We just call it the randomization condition because if it's not independent, it would not be random. They also say like an assumption of independence. I like to call it just randomization because you have to assume independence for it to be random. But we just talk about was it randomly collected. Next, we have the 10% condition, which means these 229 students are less than 10% of all students at their college. Count data means that we are asking two categorical questions. So is this a categorical question? What college did you go to? It's categories. Your birth order. What is your birth order? Well, I'm the middle child or I'm the second child. This is categories also like being the first child in your family because you would be in the category first child. So it's done categorically right here. Next, we have expected cell count. And this is where you have to be careful. You have to go to the smallest row total. Let's do that. To check this, go to the smallest row total, that's smallest column, and smallest row, multiply them, and divide by the grand total. So this is the formula. Row total times column total over grand total equals expected cell count. And so let's solve this. Row total times column total over grand total. And we have row total times column total over grand total, and we would expect, ooh, not good. Nope. That is not 5. So are all the expected cell counts at least 5? The expected cell count here, which we just need one that fails this, which is the lowest one. The best one to check is the smallest, because if the smallest one passes, they all pass. It's like the smallest one meets the standard, they all meet the standard. The smallest one does not meet the standard, so there's at least one that does not pass, so it fails it right there. Yep. So the expected cell count for professional third order in the family would be, we would expect 3.11 students in this group. Now, this is how many we observed. We saw one student, but we'd expect this. And this will be used for later calculations for cell chi-squareds, but we don't pass that condition right there. Not good. How many degrees of freedom does this have? I want you to answer this one because this is a what by what table. Be careful. This is where people usually make a small error. What this has, how many degrees of freedom? Now, the degrees of freedom formula are rows -1 times columns -1. So how many different options are there in this table for the rows? And how many different columns are there? Tiffany, great job. If this is a 4x4, and so since it's 4x4, do not include the totals. 4x4 turns into 3x3, and the degrees of freedom here are equal to 9. Great job. Yep. That's one of the easiest questions on the test. I love it. Don't use the totals. Totals don't count. Those are not options. 9 degrees of freedom. So they're going to still run the test. They probably shouldn't. They get a chi-squared test statistic, which is just like a T or a Z, and they get a p-value of 0.01. So their p-value is what? 3-letter word. The p-value here is what to alpha? So they got a chi-squared. That's just their test statistic. But that is used to get a p-value here. And their p-value is what to alpha? So the p-value here is what? The p-value here is very what? The p-value here would be very what right now? So here's your p-value. 3-letter word, the p-value is what? Because here's your alpha, which is the point at which you reject the null. It's lower. Bingo. So we reject the null. There is evidence. I reject the null because the p-value is low. There is evidence for the alternative. That birth order is associated with the college. Oh, more? Oh, and then the residuals, yeah. Examine a comment on the standardized residuals to state your conclusion. So this is going to the condition that you had. Some of the cells with expected cell counts less than 5 have large residuals. We don't really go into the residuals right here, but basically it's trying to tell you that there was a violation of a condition, and that's not good. So this literally goes back to the issue we had right here. So because we have expected cell counts less than 5, it's going to cause issues with some of the discrepancies or cell chi-squareds. So we don't talk about residuals with this, but it's important to note that these conclusions are suspect. I don't know if I would... Like, this test seems a little iffy to perform when you have a violation of the at least expected cell count of 5, because that'll cause large discrepancies in, yeah. It goes to the mathematics of it, and it's like, I don't know if this was a good idea. I don't know if we should have done this. So good stuff right there. And then let's hop back here and let's change some grades. Let's do this. We're chilling out. Chilling out right here. Drop in the next question for us to do right here. Gonna get everything fixed up right here. I'm playing 2 songs at one time. Changing grades, gotten those hundreds. If you have a question, it is time to ask questions. There we go. We are all fixed up. Drop those questions in the chat. After Canvas content number 10? Yeah, let's do some Canvas content number 10. Woo! Canvas content number 10. Last Canvas content. Oh, man. Canvas content number 10. I didn't even realize there was a number 10. The last Canvas content. Let's do 2 or 3 versions of it. The last Canvas content. Here we go. The last Canvas content ever. I'm done with Canvas content. And once again, I want to point this out. The Canvas contents are going to be super important to your understanding of the work to make sure you understand and practice for the test. Let's check this out. Here we go. We got different things right here. Let's go check out the last Canvas content. Here we go. Aw, thank you, Kayla, right there. Kind of sad. 100 points, everyone in the chat. Let's go check out the last Canvas content. Here we go. A contingency table is a key component in understanding a chi-squared test of independence. What do you think right here? Do you think a contingency table, which I've got kind of blocked out right here, what would you say, true or false, that the contingency table is important, is a key component for doing the chi-squared test of independence? Contingency tables go with mosaic plots. Contingency table shows you the counts of 2 categorical variables, where we have right here like somebody's gender and their political party, and the chi-squared test of independence is being ran down here. Mosaic plot, contingency table, and we've ran the test down here to see that they are associated, or we have evidence that they're not independent. So that is a most definite yes. That is as true can get. The results of a chi-squared test of independence conclude color choice is dependent on gender of a kindergartner. Which of the following is true? Oh. So what does it sound like they did right here? If we say that we conclude that there is a dependency between the gender of a kindergartner and their color choice, the color they choose. So what do you think they did to the null hypothesis? Did they reject it or fail to reject it? The results of a chi-squared test for independence conclude, so it comes to a conclusion that color choice is dependent or associated with or not independent. So on the gender of a kindergartner, so what do you think they did to their null hypothesis? Because they're saying we have evidence of dependency. We have evidence that there's an association between the kindergartner's gender and the color they choose. We're going to say, like, here, pick out the t-shirt, and they pick out a certain color t-shirt. There's a dependency between the gender of the kindergartner and the color they choose. We have evidence of this. So what does that mean? You can eliminate one of the worst answers right here. That's just no. Yes, Kayla, yes. So statistically significant. So what would that mean if the test is statistically significant? If the test is, this one's just a no. You look at that, no. If the test is statistically significant, what? So low p-value. These two right here, if the chi-squared test statistic is larger, like when you have larger chi-squared test statistics, what happens to the p-value as the chi-squared test statistic gets larger? If the chi-squared test statistic gets larger, the p-value is getting water. If the chi-squared test statistic is getting larger, the p-value is getting water. As I move that chi-squared over on the curve, the p-value is getting water. So as the chi-squared test statistic gets larger, which is more unusual, the p-value gets water. And that shows you why the other answer is wrong too. Because it would have to come from a larger chi-squared. It gets lower, exactly. So this one's a wrong. It says the chi-squared test statistic was very small. If the chi-squared test statistic was very small, the p-value would be very large. So since we've concluded there is some sort of dependency between the two, it would have to come from a larger chi-squared test statistic, which would give us a smaller p-value. So you can see right here that these two are actually related answers, but they're both wrong. So the p-value being higher would be from a smaller chi-squared. So by virtue of knowing that these two are connected, like if this is right, they both can't be right. So you can actually eliminate down, and then the word cause is just a bad idea. So this one has to be right here. The expected cell frequency is based on a... No, I see. These are questions on the test, and I'm sorry, but I see someone answer true, and I'm like, no. Does anyone remember for 500 points the formula? Oh, didn't put it there. 500 points, if you remember the formula for the expected counts. We were doing it earlier. This is as false can be. I'll throw you 500 points. I'll go find an expected count right here real quick. How would we find an expected count? Like if you have the counts, and I will find an expected count for you. What is the formula here? I'll draw it out. The formula for an expected count, and every single cell has expected counts. These are how many we observe. We observe from the 20 to 29 age group, 603 late preterm pregnancies. And I'm finding the expected, yeah, and you'll get that. Kayla earning everyone some 500 points. Yep, row total times column total over grand total. So I basically draw whenever I solve this, and I would have my students. So there, you get no, and you get the equations on the you get it on the final. We'll give you the equation. It's row total times column total over grand total. Great job, Kayla, right there. Row total times column total over grand total. If you notice how it connects, I just draw it on the sheet right there. So we would just solve this out mathematically to get an expected cell count for those groups. And this is going to equal to 844 times 1349 divided by 1900, and we'd expect about 600. So I expected about 600 in this group. I think that seems a little bit lower than what I would think. I'll double check my work. Well, I'll be. And let's go here and do expecteds and the mathematics. Oh, those are the... Oh my gosh. Did I just seriously do that on the total? I seriously just did that on the total. Don't do that. I was trying to do the preterm. There we go. Yeah, that's... No. I was like, that looks weird. If something looks weird, you should be like, maybe I've made an error. Oh my gosh. Don't doubt yourself. Never doubt yourself. Never doubt yourself. Every bit of mathematics we just did there was proper. There it is right there. So row total times column total over grand total. My brain just like blinked. I was like, wait, what? And I was just looking in the wrong spot. But row total times column total over grand total will give you the expected cell count. and we have expected cell counts for each of those. See, that's where you just should never doubt yourself. And so it's not based on the researcher's opinion. It is based on mathematical calculations. We've got some jump output below right here. What is the corresponding level of significance? Ooh, we got this. We got this. What is the corresponding level of significance to the confidence interval? Ooh. Who here can help out for 100 points on this one? I know people got this. This is one just like the hot dog question with the meat and the beef hot dogs. So what is the corresponding alpha level? So we've got a confidence interval right here. And if you see this confidence interval right here, really they went all crazy on this one. Of course we did something interesting. I grabbed the wrong thing. A confidence interval looks like the following. So it's saying that 85.58% is shaded in here. Oh, no worries, no worries. This is the redemption right here. So what is it asking for? It's asking for this as a decimal, though. So that's what it's asking for right here. So what is the value of that as a decimal? So it's asking what is the corresponding alpha level if we run this as a two-tailed test. So we know that that's the confidence interval. What would the corresponding alpha be? So it's wondering what... Close. You're close, but don't think of it as half. So the corresponding is not half of it, but the whole thing. Yeah, Tiffany, look at that work together. Teamwork right there. You got it. That's what it is. It's just the remaining outside portion. And then write it as a decimal right there. Remaining outside portion. So you just take and subtract from 100% and the remaining outside portion. And that should be right there. As long as we did it properly, it should just be the complement. Which of the following is not a requirement for a two-sample t-test? Condition 1. So what do you think is a requirement? Condition 1 is random. Condition 2 is 10%. 100 points right there. So if we're doing T's, which of these sounds like it would maybe not be a requirement? Who has a good guess on this one? We'll be doing the two-sample T to start next week. But which of these sounds like it would not apply to the two-sample T? And why? I think you can figure this one out if you didn't know it. But which of these would apply to the two-sample T, like not apply to it? Because the T deals with this, so you should have a good idea of which one would apply, A, B, C, or D. So which of these would not apply? I think you got it. I think people could figure this one out. Give it a second. Be like, okay, wait. We know it's random. We know it has to be 10%, less than 10% of the population. And then we pause. Yep, because this would deal with what data, Kayla? You got it. Because Mr. T is mean. Whenever you think of Mr. T is mean. So we haven't talked about independent means, but this would apply because both means, the two means need to be independent of each other. We'll go into detail on that. Rachel, amazing work. Another 100 points, Rachel. The success failure condition is for categorical data. And T tests are for the mean for quantitative data. Mr. T is quantitative, exactly. So when you see which of these does not apply, this is only for like proportion stuff. So that is it right there. You don't tell me. You don't be like Mount Pearson to me. Of course you're not. Canvas never lets me down. Let's do another version of this right here and knock it out of the park. Here we go. Another version. Is this the same thing? Sure. Same sort of questions right here. We'll try to do maybe two more versions of it. A contingency table is a key component in understanding a chi-squared. Very true. Once again, we'll just see it again. You look at the output, contingency table, mosaic plot, chi-squared test of independence to tell us whether there is an association or not between these two variables. The expected cell count is based on the researcher's opinion. Nope. It's that formula. Check out the previous thing we talked about. Row total times column total over grand totals. Row total times column total over grand total. The overall chi-squared test statistic is found by whatting all the cell chi-squared values. We can divide them, add them, subtract them, or multiply them. Well, that's going to be a tough one. Let's figure this out. Let me go get some cell chi-squareds right here. So here's all the cell chi-squareds. Values right here for the cell chi-squareds. How do you think we could obtain 7.038? Add them. The sum of the cell chi-squareds. Great job, Tiffany, right there, 100 points. So these are the cell chi-squareds found by observed minus expected squared over expected. We'll go over the formulas in class some. But we would just add together all the cell chi-squareds. Like if you literally add 2, 1, all these numbers, you will get this number down here. I'd show it, but it's kind of boring. And so we are going to add together all those right there, which is not a way to check the nearly normal. Ooh, I love this one right here. I love this question. I'm going to marry it. Chelsea said it's okay. Which of these would not be a way of checking it? Chelsea said it can. She likes this question too. I think that's it. The central limit theorem states, and that's kind of the large enough n way. So this is really like large enough n right here. That's what that's talking about. The goodness of fit test is where we use a p-value. The histogram is look at the histogram, the normal probability plot. Degrees of, we've never talked about like degrees of freedom greater than 10. So the answer is E. Remember we say like 1, look at the histogram. I think central limit theorem is just it's law of large numbers. Does that make sense? Yeah. D, it is called the central limit theorem, which is very important to know. The central limit theorem is literally, we just got to show it again. It's so fundamental to statistics because it states that the distribution of the mean will get more normal as the sample size increases. So you can see right here, the central limit theorem is this, where we have a very skewed distribution. And it's literally the law of large numbers that if we have a large enough sample, the distribution of the mean, like these data points will be taking the mean of it, will become more normal. And if the sample size is large enough, even a skewed distribution, the distribution of the mean will be normal. And so that's what it's talking about right there when it says central limit theorem. This is the large enough n condition to state that the distribution of the mean will become more normal. So degrees of freedom greater than 10 is not a way to check it right there. Good question. Calculate the test statistic. This one looks super complicated. Let's write out the equation. This one looks really complicated, but it's not. That is for exactly for quant. Great job, Tiffany. I mean, Kayla right there and Tiffany. Great work. This one right here looks very complicated till you see the equation. The top part of this equation is just a what? Tell me about the top part of this. In blue right there, the top part of the equation is just a what? All that is a what? Just talk to me about what that equation is. The top part of this is just a what? Like, yeah, large fan. The top part of that equation is just a what? That top part of that equation is just a what? A headache? The top part of that equation is just a what between two numbers? This question would definitely throw people for a loop. Just a difference. Just a difference. What do you think that difference is? Just tell me what do you think that difference is? What do you think that difference is? The difference for this is what? What do you think that difference is between those two sample means? The difference between the two sample means is probably what? Like mathematically, numerically, what do you think the difference between the two sample means is? Take a wild guess what you think the difference is. Be like, I bet the difference is this. You got it. What do we usually divide by when we do these equations? What do we call this down here? No longer a standard deviation. Oh, this one doesn't want the confidence level. This one wants what is the test statistic. It's asking what is it wants the test statistic. So this one says what is the test statistic? It says tell us what the t ratio is, the test statistic. The standard error. So this down here, this is a standard error. So what is the standard error? What is the standard error? Like numerically right now, what is it mathematically in the output? What is the standard error? So what is the standard error for this one? What is it mathematically? The standard error right now is... Do you see it? Take a look at the output. You got it. So what do you think we should just do with these two numbers? Well, we have the equation and we have the numbers. because we know what the difference is. We know what the standard error is. I know, right? You're like, hey, this problem's not so bad. Because all we do is take the difference, divide by the standard error, and that's the t-statistic. There it is right there. Oh, no worries. No, you're doing a great job right there. That is the answer. It's just the difference divided by the standard error. And that's it. Oh, yeah, Adriana, of course. Adriana, good to see you. I remember your name in the chat. Adriana, 100 points. Thank you for swinging by. Yeah, I do remember your name. Yeah, good to see you here. Excellent work, Adriana. Thank you so much. I literally say in class, like, sometimes former students swing by, and that really makes my day. I know, I do. I totally remember your name from chat. So, like, I was like, yeah. No, that's awesome. You probably remember the hair. Watch this, wait. We'll solve this one. Here's some quiz. Oh, whoa. Don't you dare. Watch this. We're going to pull some movie magic. You ready? Watch this. Here we go. Watch this. Don't go away. All right, here we go. You ready? Watch this. Welcome to Stat to One. How you doing this morning right here? How's everyone doing? Everyone doing all right? I think I got something in my hair. Just 1 second. 1 second real quick here, everyone. I totally messed it up. I haven't done that in a while. That's the long hair Brian right there. So I made that video where someone when I cut my hair and like I went down, I had it all prepared and like Chelsea and I made the video. So like I was like 1 second and I like went down. I was like, hey everyone, I'm back. So yeah. So we had that fun with that. I've got the haircut video still on here. So you can see me in the background. Hey there. Everyone, welcome to Stat to One. How are you doing this morning right here? Trying to think what else I have. Yeah, fun stuff. It's pretty fun getting to create things and just being like, let me just make something crazy right here. But yeah. No, one of the newest things we have, I always love this. I do it way too much. I probably do it like once a week, but my favorite thing is this right here. I don't know. So it's a freeze frame effect, and then I always forget that we have this right here. The things I don't use. I should put that on the main screen for when I get a problem wrong. Oh no, you should see. I just run my fingers through my hair a lot. I'm just always like, as my hair gets longer, I'll just keep doing this. I've really like, not like thin, like it's going away hair, but my hair is very, very, if I put product in it, it just completely is weighed down. Like my hair just like is very, very light. It's always been that kind of way. Like my mom, she was like, when you're a baby, I was like, you have the softest hair. She was just like, maybe that's why I do that. You know, wow. No, I don't know. Let's hope not, Kayla. I don't know, maybe. It's always been that way since I was a kid. But no, I've always like had like really, really like fine hair. Yeah, like I don't know. It's like I've gone to barbers and they're like, your hair is really fine. And I'm like, yeah, like it's happened multiple times when I go to barbers. It's just like, but it's good and it's bad because like just product weighs it down. Yeah, I know. I see some gray too. I've been noticing it too. There's like little shines of grays. Nah. No, there is. I notice it when I'm in the mirror. I can see a little shine of gray here and there, but that's all right. I'll take the gray. My beard has gray in it. My beard has gray. Like you might be able to see some sparkles on my beard. So man, I miss the thing I miss most about being a kid. In here in a little bit. If you have questions, put them in the chat. We've had a great day of doing work, and it's Haslam Friday. But the thing I miss most about being a kid is not shaving. Like this is probably like 4 days or so, and it's just like I remember being in high school and you'd be like, oh, I got to shave this month. I'd be like, okay, just like I don't know, probably horrible. I don't know. I never learned how to shave. Shiny on the beard. But I miss back in the day being like, it's like, oh, I haven't shaved in a month. It's starting to get a little stubbly. But now it's like, oh, I haven't shaved in like 3 days or 4 days. But I don't know. We all get old. It happens. It's just part of life. So there we go. Look, you can see it. It's fine. It's fine. I feel like Anderson Cooper. Anderson Cooper has got some great gray hair. Anderson Cooper is like, he's just like silver hair. That's awesome. That looks really cool. Maybe I'll do that. If I go too gray, I'll just have everything I'll just go pure silver hair. I can be like that guy. I can be the Anderson Cooper of statistics. It's my goal. It's always been my goal to be the Anderson Cooper of statistics. Has had a mustache since like the 4th grade. That's awesome. Oh, that's cool. I knew a guy in high school. What was his name? Like, that's my husband. There was a guy in high school who he was a 9th grader when I was a senior. Like, beard, like just full like 9th grader. You're welcome. Is project 2 and exam 3? You got this. You got this. We'll probably end here in a moment because I'm gonna grab a little more food. I've been feeling tired all today, and we'll knock out some project 2 here next week. Got a lot of that. So I'm gonna send out some links for the videos. But yeah, I might end just a tiny bit early today and grab some food. Food is good. Food is good. But congratulations, Tiffany. And yeah, congratulations. I think my music buttons. It's tough. Like, even I feel it at the end of the semester. You're like, man, I can't wait for winter break. But I think the biggest thing we have to keep reminding ourselves, and I tell myself this too, is like, we got this. Last week's the next full week of school. Then we get Thanksgiving break, shorter week, Thanksgiving, a little more relaxed, still come to class. Then we come back, we just go till Tuesday. So we really only have like 9 more days of class, or 10 if you include Friday. There are 10 more days of school session. Friday, week of class. Monday, Tuesday, Wednesday. Oh, it's 11 days, something like that. So we got this. We're just days away from the end of class. But I have a winter mini term. Oh, what winter mini term are you taking? And Kayla, if you want to swing by and say hey to the 201ers who are in winter mini term, because I'm doing winter mini term too, but you do get some time off. We will have off until like January 3rd. So I'll be doing winter mini term also. Fun stuff. Actually, I really like mini term because I only teach one class, and so I have fewer students. I love how many students I have, but it's when you have fewer students, you can really, like, obviously I know Tiffany, obviously I know Kayla. Like, I want to know all my students. I want to like be able to say, oh, it's so-and-so in the chat. Marketing, awesome. Yes. And just do a little practice and just email me and say, hey, Brian, can you go over this? Or can you mention this? Swing by office hours and say, hey, Brian, I was looking into this. Can you explain this? But don't worry about working a whole ton on it. Don't burn out. Hang out with your kids, hang out with your husband, have a good time. Don't worry too much about like, I got to be super prepared for 320. But I find that so exciting. Like, I'll be excited with 320 coming up right here. And we literally, as you know, end mini term on the 21st, day after my birthday, and then I'll be 40. It's my 40th birthday, and then we start class on the 24th. So we end on the 21st. We start on the 24th. So it's gonna be like that. Just start class. It's gonna be quick. So that's why, get some time, get some relax. But I'm taking 7 classes in spring for 19 hours. Oh, Tiffany. Woo! You got it, Tiffany. And I think, Tiffany, I'm really proud of you. You do the right thing. You get ahead. So you stay ahead on your material. And that way, if you hit a rough week, you guys know I talk about it every once in a while. When I hit the rough week there, I remember Tiffany, do you remember that one office hours where I ended it because I was just feeling so bad? I went and laid down and I canceled my afternoon class. It was a Tuesday. It was Tuesday that, because it was the Tuesday because I had the surgery on Monday. And so I was doing the afternoon office hours on Tuesday, and I just started to like get dizzy. I was looking at the screen and I was just getting so dizzy because I was on painkillers, and which is totally fine. I mean, you got to take them sometimes, as I found out, because I've never taken them in my life till I was like, I'm in so much pain, I have to take something. And I was just getting so dizzy looking at the screen. I was just like, I can't do this. I was like, you can do this. Just keep going. You can do this. Just like 34 more minutes. You're going to do this, Brian. You can do this. And then my body's like, you can't do this. And so I just like, I have to go, thank you, Tiffany. Yeah. I eventually was like, and then I canceled next class. Like I sent them a thing saying I laid down And then I got back up to cancel class because I went and was going to send. Actually, no, I sent the announcement to them saying, hey, we're having class. And then I sent out a follow-up and said, actually, I'm canceling it because I was like getting prepared and I was getting dizzy looking at the screen again. And I just laid down on the bed and just closed my eyes. See, if I'm going to like hang out, I usually don't lay down during the day. I'm usually going to play some video games if I have a spare moment. You got it, Tiffany. You got it. I'm so proud of all you. It's a lot, and the world is just crazy. It's tough, and it's gotten interesting as an educator because I'm here to try to treat everyone fairly, and it's tough. It's tough. There's no favorites in education. It's all about like helping each other out. It's all about being positive. You know what? Let's end off some positivity right here. It might only, I don't know who all is all watching, but if you're here, if you're hanging out for this, I don't care. I'm going crazy. We're in at office hours. I'm going to go grab some lunch. Going to prepare for the next class. 1,000 points. Hashtag show up. Just hanging out, talking about some stuff. Puppet Shark, you having a good day, man? It's having a good day. We don't see you nearly enough, Puppet Shark. With that, I'm going to go grab some food. But make sure to swing by next week. We'll be working on the project. Project is going to be probably a pretty big thing next week. Get it done. We'll have it in. Get those bonus points. And that gives a little more leeway for test 3. Moving on up. Get those points. Awesome work, everybody. I will see you later. Bye for now. Everybody, bye Tiffany. Bye Kayla. Thank you, Rachel. You're awesome. Bye, Tiffany. Bye, everybody.